Now let us discuss the equality of temperature. Consider two blocks of the same size and material, say copper. Say one is hot, i.e. the block on the right, and the other is cold, i.e. the block on the left, as indicated by the two thermometers. Now if we measure the electrical resistance of each block, they should differ, since the electrical resistivity is a function of temperature. We see the electrical resistance of the cold block is 1 ohm, and the electrical resistance of the hot block is 2 ohms. Now if we put the blocks in thermal communication with one another, we observe that the temperature of the hot block is going to decrease, and that of the cold block is going to increase. And as time tends to infinity, there's going to be no perceivable change of temperature. That is, both blocks are going to reach a final temperature, T sub F. Now, if we measure the electrical resistivity of each block after they have been in thermal communication, they will be identical. Each block is going to have an electrical resistivity of 1.5 ohms. Therefore, two bodies have equality of temperature if, when they are in thermal communication with one another, have no change in any observable property, whether that's electrical resistivity, density, or temperature. Now, this is the foundation for the zeroth law of thermodynamics. Let's consider our two blocks again, and this time a third thermometer. Let's let our third thermometer be in contact with the block on the left until the equality of temperature is established between our two thermometers. Then let's move our third thermometer to the right block, and we'll place it in thermal communication until equality of temperature is established between those two thermometers. If there is no discernible change in the mercury level of the third thermometer, i.e. the temperature is the same, we say the two blocks are in thermal equilibrium with our given third thermometer. Thus, the zeroth law of thermodynamics states that when two bodies have equality of temperature with a third, they must have equality of temperature with each other. This makes sense. If we place the thermometer on one block and it reads 25 degrees centigrade, and then we place that same thermometer on another block, which reads 25 degrees centigrade, we would assume those two blocks have equality of temperature with each other. That is, they are both 25 degrees centigrade. Now, an important distinction here is we need a temperature scale. That is, although the zeroth law establishes equality of temperature between our three bodies, what happens when we have multiple temperature devices? There isn't only one thermometer in this world. We have to use a temperature scale that standardizes our temperature measurement. We use the SI unit system, and within the SI unit system, we can use our Celsius scale, also referred to as our centigrade scale. The Celsius scale is based upon the triple point of water and our steam point. The triple point of water is taken at 0.01 degrees centigrade, where all three phases of water can exist simultaneously. And our steam point, i.e. our boiling point, is taken at 100 degrees centigrade. Now, notice the Celsius scale can go below 0. To rectify this, we introduce an absolute temperature scale, the Kelvin scale, represented with unit K. Or the Kelvin scale is often referred to as our thermodynamic scale of temperature, and it provides a scale where our temperature cannot go below 0 Kelvin. To determine our temperature in our Kelvin scale, we simply take our temperature in degrees centigrade and add 273.15 to it. Now, based upon this information, let's consider a situation where we have four thermocouples, TC1, TC2, TC3, and TC4, that are placed in thermal communication with a copper block that's being heated within an oven. The voltage output of our thermocouples is recorded by a data acquisition device, which allows our computer to log our temperature versus time. What can we say about our thermocouples? And what can we say about the block in terms of thermal equilibrium? We notice if we look at our computer, TC1, TC2, and TC4 all are reading the same temperature. TC3 is not. But since all thermocouples are in communication with a block of copper that has a pretty high thermal conductivity, we'd assume they should all exist at the same temperature. We can surmise that our third thermocouple is not working correctly. We can reasonably assume that our block is in thermal equilibrium. That is, our temperature is uniform throughout, for we have statistical significance of 3 thermocouples reading the same temperature. This is very important. When you do an experimentation or a measurement, you often rely on multiple measurement devices that you calibrate to a temperature scale. For instance, you may place all your thermocouples, TC1, TC2, TC3, and TC4 in an ice bath and ensure they're all reading 0.0 degrees centigrade. If one thermocouple is deviating, you remove that from the set before you begin your experiment.